Hello, everyone, and welcome. I'm Allan Jude, your host for today's session. I'm Clara's co-founder and head of solutions architecture. And today, whether you're joining us live or watching the recording, we appreciate you taking the time to join us. For those of you who are not familiar with Clara, we're a team of open source experts specializing in ZFS and FreeBSD, helping companies worldwide optimize their systems and tackle complex technical challenges. So you want to talk to us if you are trying to do something like build a new storage array to back a hypervisor, such as Proxmox, one of the things we'll talk about today, figuring out how to squeeze the most performance out of your ZFS or FreeBSD infrastructure, or if you're trying to develop any new features for ZFS in that environment, that's what we do. Today's session in particular is about Proxmox and ZFS, chocolate and peanut butter put together, looking at specific configurations and tunings to improve performance and basically increase the overall efficiency of your hypervisor network, as well as why you might choose ZFS instead of Ceph for your Proxmox infrastructure. So we'll talk about how to tune ZFS for performance in a Proxmox environment, the advantages of compression and caching that you can get out of ZFS, how you can use replication workflows to balance efficiency with resilience, and some of the common pitfalls we see people trip up on trying to deploy ZFS and Proxmox together. Joining us today is JT Pennington, one of our systems engineers, who has done quite a few deployments of Proxmox, and so we'll be lending his expertise to proceedings. We're also using the Zoom Q&A system, so you can use the chat or the Q&A to start asking your questions, and we'll answer those as we go along. So without further ado, let's get into the webinar.
Yeah, so the main 4 points that we're gonna touch on today are, first and foremost, how to tune ZFS for Proxmox, how to get the most out of your hardware. Proxmox is a complex system. It does a lot of things, and there are some details that you want to make sure you get right. We're going to cover compression and caching and how that comes into play with ZFS and Proxmox and running VMs and other things that you would be doing with Proxmox. We'll also be touching on replication workflows, how to improve your RPOs and RTOs using ZFS replication for failover and disaster recovery rather than just let's rsync everything back to a server. And lastly, we'll be touching on some common pitfalls that people will run into when they're trying to work out a system like this.
Yeah, so to start off, we have to look at why you might choose ZFS rather than Ceph for Proxmox.
Yeah, so there are a lot of things to keep in mind. When you're choosing a storage stack for your hypervisor, there's a lot of details and there's a lot of things that you're going to be juggling. Primarily, you want to focus on scale and durability and the trade-off of complexity and manageability. We as IT people, we love complex, intricate solutions that solve a problem, but you're going to be the one that's going to have to maintain this for years on end. So keeping something simple and efficient and effective is going to save yourself in the future. Fault partitioning is something that you need to keep in mind for how do we make sure that one error does not cascade into multiple errors that then become a larger and larger problem. And this is something that we have all seen recently with an AWS incident where one small problem, they found it, they fixed it, but then for the next 12 hours, they were chasing continual problems that were a result of the initial failure. When you're building out, a hypervisor for your enterprise, you want to make sure that you eliminate that possibility from happening by keeping in mind that when there are errors, because there will always be some errors, that they are not going to cascade and take out your entire infrastructure.
Yeah, we've all, I'm sure, seen incidents where the high availability system itself or just some distributed system was the cause of the downtime, right? Your HA system is supposed to keep everything up no matter what, but in a lot of cases we've seen in the past, the HA system was what caused the outage, and not having the HA system or approaching HA in a different way might have actually provided better durability and uptime for the service. So to that end, we're going to talk a bit about why you might want to use ZFS instead of something larger like Ceph. So Ceph has a lot of advantages, especially the fact that it can scale out. So you can add more and more separate Ceph computers to your system, and it will continue to scale and support a larger and larger amount of data. But it doesn't scale down very well. You can't have a small Ceph setup. You're basically only going to be able to have a huge one because you need at least 3 monitors, and they recommend at least 5 storage nodes and 3 managers. Now you can combine the managers and the monitors a little bit and do some tricks there, but you're very quickly looking at a very large footprint and a lot of complexity and a lot of different moving parts just to get even a relatively small Ceph cluster stood up. And then you have to think about placement groups and crush maps. And all these bits that go into deciding which blocks go where so that you can achieve that scale where you're going to be able to, oh, we need more space, we can just add more computers. And as it turns out, in most installations, even in larger enterprises, you don't need that kind of scale, right? You're not your private cloud needs to be able to scale, but it doesn't need to be hyperscale, right? You're not going to be deploying tens of thousands of virtual machines, so you don't necessarily need the ability to expand at the same kind of scale that Ceph is talking about. And Ceph has some other trade-offs as well. Because it's network-based, uh, the the latency in all synchronous writes over Ceph is fundamental to the way it's designed. There's not really a way to work around the fact that there's always going to be some latency. When you do a write, it has to be acknowledged by more than one Ceph node before it's considered safe, and you can't make that any faster. You're going to have both the network latency and the Ceph protocol latency built in there, and there's nothing you can do about it. Now, you can overcome some of that with higher concurrency, right? If you have a lot of writes happening at once, each one will still take just as long, but you'll be able to handle a lot of them at once, and it won't necessarily queue up like it would on a smaller scale system. But one of the other problems you run into is Ceph is relatively rigid because of the quorum requirements and so on. You basically always have to have an odd number of nodes. So you can't necessarily just scale your system by adding one more node. You're having to add a couple of more nodes to make sure you're keeping this number even or well, odd in particular, so that you will always be able to have, a deciding vote on, is this cluster or is that the cluster, especially as we talked about, if you have a network partition and it gets split in two. And it's a lot of different components and a lot of different configuration, and it gets really complicated to think about. On the other hand, we have ZFS. ZFS focuses on scaling up instead of scaling out. So you just add more drives to your ZFS machine or your pool, and now you have more capacity and more performance. And depending on your design, if you're doing ZFS inside the hypervisor itself, then you have much lower latency as the data is local to the machine and you don't have to go over the network. But even if you are doing a design where the storage is shared across multiple machines, you can look at that with just the network latency and not also the Ceph protocol stack latency using iSCSI or NFS to get that performance and the same kind of the flexibility to be able to migrate VMs between Proxmox nodes, but without all the trade-offs and definitely without all the complexity of something like Ceph. And ZFS was designed in particular for that lower complexity. It is, adding more storage to your hypervisor cluster is as easy as adding more RAM, right? You plug it in and it works. You're not having to go and rewrite all your placement groups and your crush maps and regenerate things and wait for storage to come online and deciding, how to redistribute your OSDs. And it can scale larger. Ceph recommends you not exceed 16 terabytes per OSD. So even if you're doing a large system where you're making a separate OSD for every disk, if you're trying to use 24 terabyte drives, you're going to have to add more complexity and split those up and make very complicated placement groups to make sure that both copies of a block don't end up on the same disk on two different partitions or something because of that upper limit of 16 terabytes in Ceph. Plus, with ZFS, you get the advanced replication and caching features that we'll talk more about later that can really push the performance and the flexibility and just the durability you get from ZFS even further. So there's a couple of different designs we can look at for a Proxmox node. The first here we called the unclustered pair. So this gives you the stronger fault partitioning by basically having shared nothing. We have, Proxmox node 1 and Proxmox node 2 here, and they don't share any resources with each other. So the first node here is going to write to the solid blue hard drives, and underneath at the ZFS layer, we're going to be mirroring that to the the not solid blue drives in node 2 that are not used for anything on node 2 by default. So we're, doing a bunch of ZFS mirrors on node 1 and storing all the data, and we're mirroring a copy of all that data to node 2, but node 2 isn't using it. And then the VMs on node 2 are writing to the solid green drives, and those are being mirrored to the not solid green drives in node 1. So in this way, if anything happens on node 1, node 2 is still working perfectly, and vice versa. And even if the network gets partitioned and the mirroring breaks down because the network went away, then ZFS uses its dirty time log and will be able to catch node 2 up when it comes back up, but it, via the transaction log on the drives, will be able to avoid a split brain problem, right? It's going to know which node has the newer information and be able to use that correctly rather than, ending up in a split brain type problem. One of the other advantages to this setup is you can do a switchless architecture. If you have a small number of nodes, even if it's 2 or 3 or 4, you can do this with 100 gigabit network cards without having to buy a 100 gigabit switch. Just by creating the ports directly between these servers, you can get all that advantage and save a huge amount of money by not having to buy all the 100 gigabit network infrastructure, just the NICs. And that, in a 4-node cluster could make a really big difference in the total cost. And if node 1 does completely fail, because we have the mirror copy on node 2, we can run those VMs and stand that back up and keep everything working. But in Proxmox, these are two separate nodes. They're not configured together. But that is, again, for the advantage of the fault partitioning. But we can also go with a different design. In this centralized storage setup, we have an actual Proxmox cluster with, we pictured 3 nodes, but you can have as many nodes as you want. And all of those are going to use the same storage, the blue active storage server there. And they're going to, most likely using NFS, but could be other things, and are going to write all the data to this main storage node. And all the data goes to the drives. Then we use SAS multipath to connect those drives in addition to the passive storage server, and then use an elastic or floating IP so that if the active storage server fails, the passive storage server can take over with a 0 RPO. So that means any data that was written to those drives, because they're directly connected to the passive server as well, when we come back up, we've not lost a single write. All the data is there, the VMs can continue running, and now you have a complete HA system for keeping your storage up and all your nodes. They're clustered in Proxmox, so you can migrate VMs between nodes, and all of the advantages you would get from some other more complicated setup, but without that complexity. You just have a pair of servers sharing a set of hard drives or SSDs or NVMe, and allowing you to create a really high performance centralized storage that still gives you all the clustering you need in your hypervisor. So after all that, nobody has any questions? I doubt that.
They're saving them till the end.
Yeah. But don't go ahead and ask the questions as we go so that we can pick good ones when we get to the Q&A section. But next up, we're going to talk about tuning ZFS on Proxmox, which I think is what most of you we're here for. So we're going to talk about how we can use these open infrastructure bits to build a really high performance hypervisor.
So like with any zpool architecture when you're building it out, how you're using your data is going to affect how you need the hardware to perform, which will then affect how the pool should be laid out. With Proxmox, with you're running VMs, that is very IO intensive, lots of small writes. So classically, we would say mirrors are going to offer the best amount of IOPS. So if you have your hard disks, you put them in mirrored pairs because you're able to read from both disks in that mirrored pair. With advancements in NVMe, that is starting to change a little bit. The math is starting to change because NVMe, while the cost is higher, the performance is so much better. And one of the things that actually gets you is the ability to move away from mirrored pairs and into using a classic RAIDZ setup so that you're able to take advantage of more of your storage capacity for data instead of just having that mirrored.
Yeah, while still getting millions of IOPS.
Correct. So just let's step back and let's explain that a little bit. Let's get into the technical details. So hard drives have one queue, and that queue can hold up to 32 commands for the drive to actually perform. SSDs also one queue, and I believe it's maybe up to 256 commands, but they're still serialized, so they can only happen one at a time on the disk. NVMe spec is way, way higher. Right now, enterprise NVMe have around 64 queues, and each one of those queues can have 64 commands in it each. So the performance factor that you're going to get from an enterprise NVMe is going to be so much greater than classic hard disk or even the highest end SSDs. We have seen upwards of 500,000 IOPS on NVMe systems. When you have that many IOPS available, you don't need to try to then cluster or to mirror your hard drives together to get better IOPS. So hard drives would typically have around, depending on your speed, 100 to 200 IOPS per disk. So in a mirrored pair, you're going to have 200 to 400 IOPS available to you. When your NVMEs have 500,000, it negates the need of mirrored pairs. And again, as Allan said, you get more of the storage that's on your disks available to you. And the other advantage is because of the price, if budget is a consideration, you can also kind of tier hard drives and NVMEs together. So you keep, say, a week of snapshots on your NVMEs for your VMs, and anything past a week, you replicate out to your disks that are in the chassis for longer term storage. And you can then, of course, tier this out to an offsite backup. You're going to keep even further retention. But if you do that, you're able to maximize the amount of storage that you have on your limited NVMe and still get all the benefits that it provides.
Yep.
Okay. So when it comes to record sizes, because this is a very important detail with ZFS, is how the record size gets set, because this is the size of the blocks of data that are going to get written to your actual disks. In some situations, smaller record sizes will be better, like, for instance, databases. VMs is another one. The smaller you can get those record sizes down, the more performance you're going to get out of system. In some situations, larger record sizes are going to be better because you're able to push more data through in that single transaction, in that single operation. Smaller record sizes will also help prevent issues like amplification. And we have done a webinar, it was in April of 2025, where we discuss the amplification problem. If you're in a situation like, for instance, when you're using NFS, it's better to have a smaller record size because you're not going to be reading and writing data continually that isn't being altered. That's a very deep topic. I would recommend you go watch that webinar if you want to learn more about that. It's well outside of the scope of this webinar. Larger IOPS, larger record sizes will also give you the benefit of better compression and better storage efficiency because it's able to put more into a block and compress it down. And when it writes to the disk, it's able to be more efficient with where it actually lays that out on disk. However, again, you don't want to go with the larger record sizes if you're doing a lot of small writes, like what you would do with a VM or with a database.
Yeah, and finding the right record size can have a big impact on performance and just how well the system performs, and just how responsive it feels to the user, and even just how much work the drives are doing underneath. Because if there's a big disconnect between what the IO coming from the VMs and what's actually happening on the physical hardware, you can end up consuming a lot more of the capacity, performance capacity of, say, the NVMEs, even though you're not actually doing as much work because of the amplification. And so avoiding that helps a lot. But if you make everything the smallest blocks, you're going to get into the pitfalls that we'll talk about a little bit later. So to try to simplify that, we have some basic starting recommendations.
Yeah, so for databases and the like, we recommend 16K. For VMs, generally 64K, 32K for very high performance workloads that you have, and bulk data at 1 meg. Again, these are just kind of a recommendation. In reality, you would want to observe your process, what your compute is doing to see what the write patterns are, to then be able to tailor your ZFS pool specifically to what your actual workload is. This is not one of those things where you just want to randomly choose a record size and just run with it. If you want the best performance, you need to test and actually investigate what's going to give you that best performance. Like all things in life, there is a trade-off if you go with one option or another, and you want to make sure that the choice that you're making is going to provide you the best benefit over time.
Yeah, compression can have a big impact here. Using a larger record size can get you more compression. And if your data is compressible enough that that's helping, in the majority of cases, then it lets you use a larger record size, get more efficiency, while at the same time avoiding the amplification because you're compressing that, 16K down to 4 8K anyway, and fitting it in. But if you're using just the smallest record size, 4K or 8K, then if you're not getting at least 50% compression, then you're writing the whole 8K no matter what. And, you can end up with a lot more overhead and not as much efficiency as if you actually went to a larger size. So it really depends how compressible your data is. So Marin in chat asks, what do we mean by amplification? So if you use the default record size in ZFS of 128K, and then your VM makes a change to its backing QCOW file that is only, 16K, then ZFS is actually going to have to read that whole 128K block, modify the middle 16K that your VM changed, recompress it, and then write out either the whole 128K or whatever it compresses down to, maybe 64K. But that meant you read 64K or 128K and then wrote that much just to make a 16K change. So now you amplified everything by 4 or 5x. Whereas if you used a 16K record size, then when you did 16K write, it would not have to read anything because we're not modifying a block, we're completely overwriting the block, and we would just write out that 16K block and there would be no amplification. The disk wouldn't have to do any additional work on top of what the VM actually tried to do. But if we go with small blocks all the time, that's that much more metadata, and we're not gaining compression, and there's a lot of other trade-offs. So it really depends on your workload what will work best. And so to that end, if you need more detailed guidance, you should check out Clara's ZFS Basecamp. This is the centralized learning site that we've created about ZFS on Clara's website, and it's a collection of over 100 articles talking about various parts of ZFS, and it's broken down based on where you are in your journey through ZFS. So if you're just getting started with ZFS, you don't know much about it, we have all the intro guides like what is a VDEV, what is write amplification, what is an L2ARC, do I want one, etc. And then we get into okay, I've decided to use ZFS. What do I need to know as I start building my first array? And then goes down into I have an array. How do I keep it running? How do I monitor it? How do I protect it? And disaster recovery and everything. So right from I've just heard of ZFS and I want to learn more through I've been using ZFS for a decade and I want to use it better. So now we're getting into some of the more interesting stuff. that we kind of just briefly touched on, compression and caching, and how to minimize your data and optimize access. So one of the biggest advantages to compression is the reduced storage footprint. Right? If we have, say we did, as we recommended on the previous slide there, we used a 64K record size, or as Jonathan in the chat room asked about, using the same vol block size on a ZVol, then we're going to take the multi-gigabyte or however big your virtual machine image is and break that up into chunks of 64K. And then each of those chunks independently will get compressed. And so if it's empty, it'll compress to 0 and it's basically free thin provisioning. But if you have some data in there, maybe it compresses down to 16K or 32K or whatever. But if you can actually achieve that level of compression, where most 64K blocks actually compress down and only take 32K of space, then not only do you save half of the storage that the VM was using, so you have that much more storage for another VM, it also effectively doubles the bandwidth of your disk, right? If we're reading a block off of, say, some SATA SSDs that you're using for your array, and they can do, say, 400 megabytes per second total. But if we're getting 2-to-1 compression on all those blocks, we can read 400 megabytes of compressed data off each SSD, and then we decompress that with a bit of CPU, and now we're getting 800 megabytes per second off each SSD. And if we have a dozen SSDs in the machine, suddenly we can do some really high bandwidth, even though we're only using SATA SSDs, not high bandwidth NVMe. So immediately, compression is going to help you increase throughput. In the past, we often considered compression to add latency, but with LZ4 and Z standard, the decompression rates are super fast. LZ4 can easily decompress 10 gigabytes per second using even a modest CPU. And Z standard, what's really nice with it is even if you use the absolute craziest level of compression on writes, which we wouldn't recommend for VMs, but if you're archiving stuff, can make sense. No matter what level of compression you use for the writes, on the readback, you get the same speed no matter how compressed the data was. If the disk can provide the data fast enough, the CPU will be able to decompress it without using a lot of effort. And that allows you to scale with the number of CPU cores and get huge bandwidths out of your compressed data. So that improves the logical throughput and headroom, right? If your SSD can only do 400 megabytes a second and you have 600 megabytes a second of load, if you're using compression and you're only using 300 megabytes now to achieve that 600 megabytes of logical throughput, you still have 100 megabytes of headroom left. So even if the next workload doesn't compress, you still have some room. But one of the other big things is the compression also improves the caching. So ZFS will use the ARC, the adaptive replacement cache, to keep the most recently and frequently used blocks in RAM rather than in addition to on disk, so that it can serve them to you faster. But it will keep the compressed version in its cache. So that means if you're getting 2-to-1 compression as well, then you're going to be able to cache twice as much data in RAM. And so that's twice as much data that's going to come from RAM instead of off disk. And that, again, further improves the performance of your system basically for free using ZFS. Tanner in the chat room asks about recommend CPU pinning for NVMe systems. That can be quite helpful. So each NVMe will have some queues, usually spread out across the CPUs. It depends. So if you have just 1 or 2 NVMe devices in your system, normally what your operating system will do is say, all right, we're going to do like 8 queues for each NVMe, and we'll pin each queue to a different CPU. And so if you have 16 CPU cores, that'll work out nice. But if you're doing a higher end system where maybe you have 24 NVMe drives, you're not going to want to do 8 times 24 necessarily. But having those NVMe queues spread across the different CPUs can help to make sure that interrupts from each NVMe are spreading that load out and ensuring that you get the fastest possible response times. But you might want to keep some CPUs not receiving interrupts from the NVMe so that because interrupts are a very high priority thing that are going to push off other parts of the operating system and other code from running, you might want some CPUs that are dedicated to handling the other things that have to happen on the system. and possibly adjusting the interrupt moderation on your NVMe to avoid creating too many interrupts, to lower the CPU usage caused by the NVMe in exchange for a little bit of extra latency, knowing that the NVMe latencies are so ridiculously fast, it's not necessarily helpful to get notified immediately that each IO is done if you're doing a million IOs a second. Maybe you don't need to be alerted a million times a second. So that one's a more complicated question, but definitely something that Clara can help with if you're interested in having a performance analysis of your NVMe system to tweak it to get the best performance you can. Because at the same time, you also want to make sure that the performance of your storage isn't hindering the performance of the VMs themselves as well. And then on the caching, we talked a little bit about the ARC. It basically stores the most frequently and recently used data. So every time you read a block or write a block in ZFS, it's going to be stored in memory as well, because the data you just wrote or the data you just read is the most likely data you're about to read a second time. So either you wrote it and you want to read it back, or you just read it and something else is going to read it again. So that's why we cache the most recently used data. But if you do something like, every night you run a backup, having a cache that only looks at the recently used data will just constantly churn itself as you do a backup, right? Because you read every file. And so it's going to have to evict things from the cache to make room for the new things. ZFS protects itself from that by splitting the cache and having some of it be the most frequently used files. It's like, hey, you've read this block 1,000,000 times in the last day. I don't think you're suddenly going to stop reading it. So let's not let that be pushed out of the cache for something that you read an hour ago and maybe you will read again, but is less likely than this file you've already accessed 1,000,000 times. And then ZFS's algorithm will dynamically adjust the split of like how much frequently used versus recently used it keeps, and it'll kind of slide those back and forth based on the usage pattern of your system. So as if you frequently access more data, it's going to make that a greater percentage of the cache and adjust dynamically to give you the best performance. But if you don't necessarily have enough RAM in order to cache everything that you're going to need, you can look at the L2 arc, which basically says as data is about to be evicted from RAM, from the cache, because we need to store something else that maybe looks like it'll be better, we can write a copy of that to a fast device like an NVMe so that if we have to read it back, we can get off that fast device instead of a slower device. And that can help as well, although that has some overhead of its own. And if you try to have too much L2 arc, each entry in that L2 arc takes away from the arc, and you can actually end up making your performance worse. So you have to consider how you're sizing that quite carefully. Jan from the chat room asked, does ZFS cache metadata from the pool in the arc? And yes, it does cache the metadata from the pool as well. And that's oftentimes that most frequently used data. Because if you have a big QCOW file used by Proxmox, the upper level metadata that describes that whole file, you're going to access that every time you read any block in the file. And so the top couple levels of metadata are going to be used super frequently on a busy VM. And so ZFS will keep those in memory in that frequently used section. They'll be really hard to dislodge in favor of something that you're not using as much. The other interesting feature in ZFS is the prefetch algorithm. So if you're reading some data, it is likely you're going to read the data that comes after that as well. So ZFS will then start looking at the usage pattern and say, the last couple times you read something, you then read the block after it too. And so it might issue extra reads to read that next block as well, so that when you go to use it in 10 milliseconds from now, we've already have a copy in RAM and we give you faster data. And then every time that works, right, every time we get a win from that, it expands how far ahead it will read in that file. So this is to try to avoid the problem of if it's something like a database and our access is truly random, then prefetch can be bad, right? If we're reading more data than we need to, then that's wasted work. So a lot of consideration based on your workload has to go into deciding whether prefetch is going to help or hurt. The algorithm is pretty good, but you can always, a human might know better. And that's why ZFS now allows you to adjust the prefetch per dataset or zvol so that you can decide, hey, this VM has a database, no prefetching. This VM is doing your Windows file server or something. It's going to have lots of prefetch. Let's use that. So now we're getting kind of into some of the questions we have queued up here from Alexander, talking a bit about how replication will work and how to use that to improve your HA. So whether you're using a single node setup, like literally just one Proxmox machine with ZFS running on that machine, and that's your whole hypervisor, maybe a home lab or something, uh, even if you're using something as simple as that, or you're doing the one we pictured before with 8 Proxmox machines in a cluster feeding into an HA pair of ZFS for high availability, either way, you still need backups, and you want efficient and consistent backups. One of the problems with most backup software is they back up progressively, right? You start your backup and then you read this file, then that file, then that file, going through. Or even with a large VM, you're reading the VM while it's still changing. And that means you get an inconsistent backup. The backup of the first VM is from a different time than the backup of the last VM. Using ZFS's snapshots, you can create a consistent backup where you back up everything at exactly the same moment in time. Using ZFS replication, you can now keep a copy of all that data at a second site. So you can have asynchronous replication to a disaster recovery location where now, those two machines that were holding all your VMs, an exact copy of that data that's only ever 15 minutes behind is now at, your second office across town. And that can really help things quite a bit. And it allows you to have your recovery time objective and recovery point objectives be 15 minutes or less and keep things really tight that way. But, to answer Alexander's questions, can we explain a bit more how the HA for the storage works? Having virtual IPs with NFS is great, but how do you make sure data is replicated in real time? And how VMs with databases and so on NFS will perform during the storage switch and how to optimize the storage. So in the design we pictured before, I guess I can quickly jump back to that. So in this design, we are not using ZFS replication. These drives are using SAS multipath and are physically connected to both the blue and green storage server. And the floating IP switches if the blue one goes down, and the green machine has access to the exact same hard drives that have all the data in real time. And so that allows us to have real time, there's no replication. It's actually sharing the same physical hard drives and ensuring that we have all the data. And then for disaster recovery, we then replicate all these drives or all the data in this pool to a second location. And that one, as we said, might be up to 15 minutes behind. But, if this building burns down, 15 minutes is a pretty good window. In this setup, again, we're not using ZFS replication. We're actually doing mirroring directly between the two pools. So we're using something like iSCSI or RDMA to basically in real time, every write that happens to this blue drive also happens to the second blue drive. And that way the data is always consistent. We can use replication, but as you say, it's always going to be at least a minute or two behind, and that might cause a problem for a VM that's hosting a database. Although in particular, if you're worried about a database, it might make sense to look at doing the HA higher up at the database level, right? Postgres and MySQL have their own HA systems that allow you to keep each of those nodes or multiple separate database nodes different. So instead of actually relying on if node 1 dies, we can start the VMs from node 1 on node 2. If instead you put a database on node 1 and a database on node 2, node 1 using the blue drives, node 2 using the green drives, and have the database handle the replication of the data there, then you can get much more consistency and a much lower failover time that way, and a much stronger RPO. But you can use ZFS replication. as a less costly setup. As we said, HA is often the thing that ends up taking out your performance or causing the downtime. And because of that, using replication, where it's like, okay, if the system goes down, um, we are going to try to get it back up. And if that is going to take more than 15 minutes, we're going to decide to fail over to our copy that's another 15 minutes too old, but that gets us back up, and a human made that decision, and then we can solve the problem later. Whereas an HA system that fails over automatically always has a chance to go wrong and cause a bigger outage. And those second order outages where the system that was supposed to prevent the outage caused the outage often take much, much longer to resolve.
So when it comes to ZFS replication, there are tools that will make your life a whole lot easier. Tools like Syncoid, zRepl, or BZFS. These are the things that we recommend. We understand that there is a temptation to just rolling your own and scripting it out. And the problem is there will be edge cases that you will be running into for the rest of your deployment. We really strongly recommend that you stick with the existing tools, because those existing tools have had years of effort in them to address those edge cases that you will eventually run into. The temptation is there to do it yourself, but this is one of the cases where your future self will thank you if you take the well-worn path and you don't try to create your own infrastructure solution around this. Another thing that you can do is you can use bookmarks. This will help reduce the storage costs of snapshots on your primary node. Allan, can you give kind of a good, clean, succinct explanation of what a bookmark is and how someone would use it?
Yeah. So normally you have a snapshot, which is all the data at a certain point in time. So on a certain transaction group, it's going to retain any block that gets changed after you make the snapshot. So when you overwrite a block or create a new block, it'll be over here, but any data that would become free space normally is kept by the snapshot. A bookmark contains only the time of the snapshot, but doesn't keep the old copies of the data. So this allows you to keep the common point between pool A and pool B for replication, to do an incremental from the bookmark to some later snapshot without having to keep the old data that's already been replicated. So if we take snapshot A and then take snapshot B, and we replicate A to the other machine, and then we can create a bookmark out of A and delete it, freeing up that extra space on the first server, but still use that bookmark to replicate the difference between the first snapshot and the second snapshot to the other server.
And I believe you can only have one bookmark. Is that correct?
No, you can. That's a checkpoint. You can only have one.
Oh, check. Okay.
Bookmarks. Every snapshot can be turned into a bookmark, and it allows you to basically keep the ability to do an incremental from it without having to keep the old data that is already been replicated. And that allows you to then change the frequency of your snapshots to get whatever recovery point objective you want, right? How much data are you willing to lose because your backup can't ever be as up to date as the copy of the server that went down? But with ZFS replication and snapshots, you can get that window down to under 5 minutes. Whereas, if you're looking at your traditional backup system that ran once every night, your recovery point objective could be up to 24 hours. Or worse, if the backup was running when the system went down, your new backup isn't actually done. So now you're looking at like a 30-hour recovery point objective, because the last backup that completed was more than 24 hours ago. Whereas if you're using ZFS with replication, your last backup that completed could be as little as 5 minutes ago. Every 5 minutes. So next up, as we promised, talk about some of the common pitfalls, and that gets right into Jonathan's questions about ZVols. So the default in Proxmox when you use zvols to back a VM is to set the block size to 8 kilobytes. That was the default in ZFS in the past, but Proxmox still sets it manually every time you create a zvol. Whereas ZFS changed its default to 16K back in 2021 because it'll be that much more efficient and you get a lot more advantage out of the compression. The biggest thing is if you have the smaller vol block size, that means ZFS needs twice as much metadata to keep track of, every 8K of that zvol instead of every 16K. If the zvol is the same size, that's twice as much metadata. And that means every time you write one of those 8K blocks, because ZFS is a tree of blocks, you have to update all the parents all the way back to the top of the tree. So that might actually mean you write more metadata than data every time you write to the zvol, and that can really hurt your performance. Also, as we start looking at possibly using NVMe in RAIDZ instead of mirrors, because we want to get more of the capacity from the expensive NVMe, and the IOPS are still going to be good enough that that'll work, really small blocks in RAIDZ can be really inefficient because every allocation has to be a number of sectors that's divisible by the total stripe width, which will be, your RAIDZ level +1. It means that, especially with RAIDZ 1, 8K might be super inefficient and mean that it actually takes more space than it needs to for each block. And getting a vol block size that aligns well with the width of your RAIDZ can also make a bigger difference, both on avoiding not so much amplification, but the wasted space from padding, and obviously the bigger size allowing compression to do more work for you. And yeah, the small block size causes more metadata, more indirect blocks, which has both a capacity and a performance impact. But obviously, the biggest pitfall we see people running into is trying to host VMs on hard drives. That's always going to be quite slow. You can mitigate this at least somewhat by using a metadata VDEV. So all those metadata and indirect blocks, in order to read any random 8 or 16K chunk of a zvol, you have to traverse that tree of blocks to get to it. And the top levels of those trees are going to be accessed often enough that'll be in the arc. But so that kind of second to last layer is probably not. And so if you're having to read completely cold one block off of your zvol, in ZFS, you're going to have to read the top level block and the next, all the way down to it. If each of those reads takes 5 milliseconds on a hard drive, suddenly that means that one cold read will take 25 milliseconds. Whereas if we keep all those indirect blocks and metadata on a fast device and then just the data on the hard drives, that same read would only take 5.5 milliseconds. Because the first 5 reads, instead of taking 5 milliseconds each to randomly seek around on a hard drive, are going to read from an NVMe or an SSD in 0.1 milliseconds. And then we just have the one 5 millisecond read from the hard drive. Plus, you almost certainly in anything where you're hosting VMs are going to want a SLOG, a separate log device in ZFS for its intent log. So those fsyncs that the VM is doing get to go to a fast drive first while they wait to be synced out to the slower hard drive in bulk. Because batching all those together into a big write is much more efficient on a hard drive. If you're writing 1 megabyte chunks, a hard drive can do 250 megabytes a second. If you're writing small blocks, a hard drive will struggle to do more than a couple of megabytes per second, and it can really tank your performance. So I think we have time for 1 or 2 more of the questions.
Yeah, we got a bunch of good questions in.
Yeah, so I'm going to hit Nick's
here.
first.
Go ahead.
So Nick says, with the Proxmox cluster solution mentioned before, are there any practical throughput or IOP constraints on the shared storage pool? I've used that with spinning drives before, but wonder about issues with bottlenecks with flash. It depends. You can run into bottlenecks with your disk controller, like your HBA, if you're using one. But if you're doing something like NVMe-over-Fabric, that can be basically a separate 100 gigabit connection. And so not necessarily, there's nothing inherent in the design, but there may be specific bottlenecks inherent to the hardware that you choose. So if you need help with that, definitely reach out to us. So actually, I'll bring that up here. This QR code will take you to our ZFS storage design solution page, where you can reach out to us and tell us, I'm trying to build a system for this type of VM and do this, and we can help you pick the right hardware or adjust the hardware you have, and kind of solve these bottlenecks during the design phase so that your system will actually be able to get the performance that you need to hit your goals for the performance and make sure that you have a good experience using ZFS. Uh, JT, did you have a top question you wanted to ask?
Well, yeah, there's a good one that I think is really important. That it's a kind of a quick one we can cover, which is Bruce asked about the scarcity of hard drives because of big data center build-outs and settling on refurb drives. So I thought we should probably touch on the difference between refurbed and recertified because that is a very important
Yes.
distinction.
Yeah. So we've seen pretty high lead times where, like, if you want a hard drive, you might be looking at 6 to 8 weeks to get it ordered, but have not seen quite, complete inability to get drives. But to JT's point, we have worked with other partners with recertified drives. So normally, manufacturers build hard drives and they put them through a bit of QA and they pass that and they go onto a store and you buy it or to a distributor or whatever. Then there are drives that fail QA at the manufacturer and then they go and work on it some more and fix the problem. So these drives are called recertified, and they are still, 0 hours used, but have basically gone through additional testing at the manufacturer because they're, the first QA level found a problem. They fixed that problem and tested it some more and are honestly even more sure than the retail drive that this drive is good. Then there are refurbished drives. That is a drive someone had a problem and returned, and maybe they got it working again. That's not the same thing. Those can be okay too, but recertified is still new, whereas refurbished is someone else used this for a while and it's been shipped back and forth a bunch more. So when you're deciding, recertified can be that really sweet spot on, you're still saving a lot of money over other drives and they tend to be available right now, like will ship tomorrow, uh, but don't have the same risk that a refurbished drive does.
The other thing to keep in mind is the term refurbished is very loose and it gets kind of bent by a lot of different vendors into what it actually means. We recently have been working with a client who went and got some refurbished drives as the vendor claimed, and they had 50,000 hours because they had been drives that were used. The seller refurbished them and then sold them off to another person. So you really want to be careful to make sure that when you are buying drives, you are buying them from a very reputable source. Let's see. Is there another quick one here? Yes, we had one from Tomas. How much space should be reserved on a pool to prevent performance degradation? And what is the compression that is probably optimal for VMs in general?
Right. So reserve space, you don't need a lot, 5% or so. So generally how we do that is just creating an empty data set and setting a reference reservation on it for something about 5% of the pool. I oftentimes make that a little higher, like 10 or 15%, so that the load disk space alarm in my monitoring system will go off early as we approach that. And then I can decide to either, clean up some snapshots or prune some old VMs or release some of that space from the reserve. But this way, as we start to run out, I get that the warning ahead of time. Because as we were just talking about, if it's going to take 8 weeks for new hard drives to come, I might need a little bit more heads up that I need to order hard drives early. And maybe one very last question. Mike asks, what's your recommended metadata VDEV or SLOG setup? Three-way mirror of high write capacity NVMe's? Generally, for metadata, for sure, a three-way mirror, or basically the depth of the mirror should match the parity you do on the rest of the pool, the main data. So if you're using a RAIDZ 3, you'd actually want a four-way mirror even. The SLOG, you probably only need a two-way mirror. High endurance is good. The kind of complexity with slog is you don't need a lot of slog. The drive doesn't need to be very big, but bigger drives have better endurance. So oftentimes getting a big drive will give you that more endurance, maybe at a better price point than a much higher write endurance device that you could buy in a smaller size. So that can be a bit of a trade-off. And again, check out the QR code here. We can help you pick the best drives for your use case, whether that's, SLOG, you definitely need that. L2ARC, you don't necessarily need the endurance. If they die, it's just a cache, it's not a big deal. But metadata is everything. If that dies or even degrades, it can hurt the whole pool. All right, I think that's about all we have time for, but thank you for attending today. And if you need to reach out to us, we can be reached in the various places listed here. But thank you all for joining us today, and hope you found this decision insightful. I did want to, hold on, there's a poll I meant to launch. Poll launch. There we go. Get your votes in for the poll here. But if you have any follow-up questions or want to learn more about how Clara can help you with your ZFS or FreeBSD needs, definitely get in touch with us and let us know. Be sure to keep an eye on our webinar page. We've actually announced the next 2 webinars for November and December already, so you can go ahead and sign up for those now. And obviously, as we said, we have articles coming out all the time, and you should definitely check out the ZFS Basecamp if you want to learn more about ZFS, and we'll be putting more in there about Proxmox in the future as well. So we hope to see you again next time, and thanks, everyone.
Yeah. Have a good day.